So today we're talking about chemical reactions. A chemical reaction, generally speaking, is just some process that's going to create new materials with new both physical and chemical properties. In other words, what you start with and what you end with will have two different sets of characteristics. The materials that we begin with are typically called the reactants, and the materials that we end with are the products. They are the ones that are produced. One of the things we want to look for, one of the ways we can tell that there's a chemical reaction going on, is certain signs that appear. In a rapid chemical reaction, and this is kind of critical because a slow chemical reaction, these may not be easily perceptible, but in a rapid chemical reaction, there will oftentimes be a change in color. Now, this could be the appearance of a new color or the disappearance of a color. Simply having a color diluted, for example, when you put food coloring into water and the water seems to become blue, if the food coloring was blue, is not a chemical reaction because the blue color was already there. If you mix two clear liquids together, though, and you get a blue color, then that would indicate some sort of a chemical reaction going on. Another classic component is release of a gas, bubbling. Now again, you have to be careful. Boiling, for example, produces bubbles, but that is simply a state change. That is the liquid form changing to the gas form. So we're talking about two materials coming together and producing a gas because of their interaction with each other. A temperature change, in most cases, this is going to be a release of heat. Sometimes it can be an absorption of heat, but most of the case it's what we would call exothermic. It's going to release heat. We could also talk about energy release, light. That would also be an indicator that something has happened. And finally, formation of precipitate. If you take two clear materials and mix them together, and suddenly they turn cloudy. That cloud is usually formed from a non-soluble solid appearing. That's precipitate, just like rain is precipitation or snow is precipitation, something falling out of the sky. This is also something sort of falling out of solution. Chemical reactions occur for the simple reason that the elements, generally speaking, are trying to complete their octets. They will combine to reach a full octet. Now there's an additional component typically involved regarding the energy of the products versus the energy of the reactants. But if you can typically think that they're going to react so that everything has full octets and meet the octet rule, that's a good general rule of thumb. Now, when it comes to actually describing chemical reactions, there are a couple of ways we can do that. The main way we do it is, and what large part of this is about, is using what we call chemical equations. These chemical equations are sort of the sentences of chemistry. If you think about the elements as being our letters of the language, compounds as being the words of the chemical language, and now chemical equations are how we put those words together to make sentences. We typically have two different ways that we can do this. One is in a word form, and so here we write out simply the names of the chemical compounds. So we react calcium with oxygen to make calcium oxide. That's useful in some ways, but it's not as useful as we would like it to be. A couple of notation pieces in here. When we write the plus, when we have a plus sign in there, that is going to indicate that there is a combination of those materials. They are both present. So in this case, these two combine together, and the arrow indicates that we went from these materials on the left, the reactants, to these materials on the right, which are the products. Now, the more important and more useful way of writing out these equations is in terms of chemical formulas. So a chemical formula, we use our chemical notation and write out the form of the chemical compounds. So here, calcium is an element, so we write its elemental symbol, plus oxygen. Remember, oxygen is one of our diatomics, so it would be O2, and that's going to make calcium oxide. Now, one of the things to remember with this is that, first of all, it's much shorter than writing out the full names. Second of all, it's going to help us later on when we start talking about trying to calculate amounts of chemicals in a chemical reaction. One thing that we do need to be really careful about, though, is making sure we have the right formulas. The chemical compounds have to be properly written out in order for our reaction to be accurate. So that's something that you really have to pay attention to as you go through and write out these equations. So let's take a look at an example. What would be the formula equation for the reaction between magnesium and nitrogen to produce magnesium nitride? So our starting materials, our reactants, are magnesium and nitrogen in their pure elemental forms. So those would go on the left side of our equation, or our arrow. On the right side, the product side, we're going to have magnesium nitride, which is a compound. Remember, we know that it's compound because of that IDE ending. So if we write out magnesium and nitrogen in their elemental forms, magnesium is a metal, nitrogen is one of our diatomics, so we have to make sure that we write that correctly. Now, when it comes to the product, magnesium nitride as a compound, the fact that magnesium is a metal should be a tip-off that this is an ionic compound. With ionic compounds, remember, we always have to make sure that the charges are balanced so that the positives and the negatives, the cations and the anions, create a neutral combination. So right now, if we look at magnesium and nitrogen, magnesium is a +2 charge, nitrogen in its ionic form is -3. So remember, we can take those numbers and cross them down in our cross method to determine what the subscripts should be in the proper compound of magnesium nitride. So the proper formula for magnesium nitride should be Mg3N2. And that would be the correct formula for that compound. Now what about this example? Silver nitrate reacts with copper to form copper-2 nitrate and silver. You may recognize this as a single replacement reaction, if you've talked about that already. Silver is a pure metal, so again, this must be an ionic compound, so we would have to look at charges. Silver's elemental symbol is Ag. Nitrate, the ATE ending, remember, is a good indication that you want to look at polyatomic ions, complex ions, not just at your elements. And if you look at nitrate, you'll find NO3 with a -1 charge. So 1 silver to 1 nitrate combines with copper, just pure copper, so it's Cu. And then we make copper-2 nitrate. Remember, this Roman numeral 2 tells us the charge on the copper was +2. So if copper is +2 and nitrate's only -1, then we have to make sure that we get 2 nitrates for the 1 copper, and then pure silver. So here is the word equation, and this is what the formula equation would look for. Again, notice we had to have 2 nitrates to balance out the copper because the copper was +2 and nitrate is only -1. Now, here's one of the critical things. When we write chemical equations, they have to be balanced. In some ways, it's similar to a mathematical equation being equal on both sides. In this case, this is because of the law of conservation of matter, which says that in a normal chemical reaction, not a nuclear reaction, but a normal chemical reaction, atoms cannot be created or destroyed. Matter cannot be created or destroyed. So, if we take a look at the first example we did, it becomes obvious when we start looking at both sides of our equation that the materials are not the same. We have 1 magnesium in the reactants and 2 nitrogens in the reactants, because it's in 2. But in the products, we've got 3 magnesiums to only 2 nitrogens. So to fix this, we have to balance our equation. We have to make sure that we have the same number of each element, each atom, both in the reactants and in the products. When we do this with coefficients. Coefficients, remember, are the numbers in front of the number of elements or compounds. We have to do this in front to change how many of that particular element or compound we have, because if we change subscripts, we're changing the actual chemical formula. When we want to calculate the total number of each element, we multiply coefficients by any subscripts. But we never, ever change the subscripts once we have the basic formulas down, because changing the subscripts changes what the chemicals are. And once we've got the actual chemicals written out, we have to work with that. We can't go changing it. So, if we look at a nice example from our PhET website, okay, this is phet.colorado.edu. They have lots of great apps there. This is one of them. If we're making, this is a little different from our reaction, we're making nitrogen and hydrogen. We're using them to make ammonia, NH3. And the nice thing about this is it gives us a little particle view. You can see N2, we have two blue objects representing the two nitrogen atoms. We have the two white objects for the two hydrogen atoms. And then in the products, we've got one nitrogen to our three hydrogens. So it becomes pretty obvious that from that particle view that this is not balanced. If we use something like this scale model, these balancing scales, that also helps to sort of point it out. We can see that if the fulcrum here represents our division between reactants and products, we have two nitrogens in the reactants and only one in the products, while we have two hydrogens in the reactants and three in the hydrogens in the products. Neither of them is balanced. When we work with these, remember, all we can do is change these coefficients out in front. So we're going to use that to try and bring everything into balance. So we have the same on both sides of our equation, both in front of and behind the arrow. Let's start with the nitrogens. We have two on the left, but only one on the right. The only way we can change that is by increasing the total number of these ammonia molecules. We can't put a subscript behind the nitrogen. We can't make it N2H3 because then it's no longer ammonia. We have to stick with the NH3 and just create another molecule for that. Notice when we do that, that brings our nitrogens into balance. Our hydrogens, however, become even more out of whack because now we have 6 on this side and only 2 in the reactants. But by adjusting how many of these we have in the reactants, we can make it so that we have the same number on both sides of our equation. That is a properly balanced chemical equation. That is a happy equation. So we're going to do that with our example that we had before. So here was our original equation, our original setup. We have to pick a place to start, and there are some general rules that will usually help you out. In this case, we're going to start with a metal that appears only once on each side. So that means the magnesium. When we look at that, we see that we've got 3 in the products and only 1 in the reactants. So we're going to change the coefficient in the reactants to make sure that we get the same number on both sides. So we put a 3 in front of the magnesium, and that gives us 3 in the reactants. We already had 3 in the products. Now we take a look at the nonmetal, the nitrogen. In this case, we started off with 2 nitrogens in the reactants. We ended with 2 nitrogens in the products. So we're balanced and everything is good to go. We're happy with that. When you balance an equation, here are some general steps to keep in mind. Generally speaking, it's usually easier to start with metals, partly because metals typically only appear once on each side of the equation. It's not always true, but it's a good general rule. So start with a metal that only shows up once on the reactant side, once on the product side. And then once that one's balanced, find a new metal and keep doing that back and forth until all of the metals in the reaction are balanced. Then start with nonmetals, leaving oxygen and hydrogen till last, because oxygen and hydrogen are commonly found multiple times on one side or both sides. So those are the hardest ones to balance. So once you have all the other nonmetals balanced, then start with the hydrogen or the oxygen. Again, look for whichever one shows up only once in the reactants and only once in the products, because that will be much easier to balance than trying to fix something that shows up in multiple places. And then finally, once you've got everything done that you can that shows up only once on each side, then finish up whatever's left. And at that point, it should be fairly simple. So let's do one more quick example. So methane is a combustible gas. In the presence of oxygen, it creates carbon dioxide and water. If we write the word equation, it's going to look like this. Methane plus oxygen gas to make carbon dioxide and water. The formula equation. Okay, methane, we haven't really talked about this one yet, but methane is CH4. Oxygen is O2, because it's another one of our diatomics. Carbon dioxide, remember the di prefix tells us two oxygens, so it's C1O2, we don't bother to write the 1, and then water's formula as usual is H2O. So now let's balance this equation. So here's our basic equation. We have no metals, so that leaves us all with nonmetals. The only nonmetal that is not hydrogen or oxygen is carbon, so let's start with that. So if we look at the carbons, we have 1 in the reactants, we have 1 in the products. Hey, that's good. That's balanced. So now let's take a look at the hydrogens and oxygens. The oxygen appears once in the reactants, but it appears 2 different places in the products. That's going to make it a little trickier to balance. So let's focus on the hydrogens, because the hydrogens only appear once on each side. So in our reactants, we have 4 hydrogens, 4 times our invisible 1. And in our products, we have 2 times our invisible 1 coefficient. That tells us then that we're going to need a new coefficient in front of our water here, so that when we multiply it by 2, we get 4, so that we have the same number of hydrogens on both sides. And what times 2 equals 4? 2. So we put the 2 out in front. So we've got our carbons down, we've got our hydrogens down. Now we need to finish off with our oxygens. So if we look at the reactant side, we have 2 oxygens here, but on our product side we have 2 here, plus an extra 2 from the water. So that gives us a total of 4 over here. So again, we need a coefficient out in front of our oxygen here, so that when we multiply it by 2, it equals 4, which means that, again, we're going to need a coefficient of 2 out in front of our oxygens.